Alright, so the next lesson we're going to talk about is on concavity and the second derivative test. So we're going to define concavity first. So this is a mathematical definition. So we're going to say let f be differentiable on an open interval. We'll call that interval I. And then the graph of f is concave upward, which we'll just, moving forward, call it concave up on I when f prime is increasing on the interval, and it's concave downward, which we'll just, moving forward, call it concave down on I when f prime is decreasing on the interval. So let me give you a quick little picture of what that means. So here I'm going to draw two pictures. One demonstrates something going concave up. So I'm going to first draw a picture here in black. If something is concave up, that means at points on this graph, the tangent line has a positive slope. That means f prime, the derivative, is increasing. So this picture represents something being concave up. If something is concave down, then it's going to look the opposite. It's going to have tangent lines that are decreasing. Well, that one's not even on there. So this picture represents something that's concave down. So now I have a theorem for you. It's all on concavity. We're going to call this theorem 3-7. And I'm going to switch this to be back to the gray. Theorem 3-7. We're testing for concavity. So we're going to start by saying let f be a function whose second derivative exists on an open interval, which we'll call I. Then we can say the following things. The first thing, if f double prime, meaning the second derivative, is greater than 0 for all x values in our interval I, then the graph of f is concave up on that interval. We can also say if the second derivative of x is less than 0 for all x in our interval, then the graph of f is concave down on the interval. So I'm going to give you now, let me redo that. I want that to stay that color. I'm going to give you a little footnote on how we can use this, and I'm going to do it in a different color. I'll do it here in this maroon color. So to apply theorem 3.7, we need to find the x values that make our second derivative equal 0, or We need to find the values where the second derivative does not exist. And then we are going to use these for our test intervals. And then we are going to test the sign of the second derivative in each of those intervals. So I'm going to now look at an example. It's our first one, example 1. We are going to determine the intervals on which the function is concave up or concave down. And our function is going to be f of x equals 6 over x squared plus 3. So when I'm doing this particular problem, I'm going to actually rewrite f of x so I don't have to have some stuff in the denominator. So we're going to rewrite it as f of x equals 6 times x squared plus 3 to the power of negative 1. And that's fine to do. You don't have to do it that way, but then you have to use the quotient rule when finding the derivative, and it gets a little weird. So now that we've rewritten it, we can now find the first derivative. We can find f prime of x. So we're going to bring that negative 1 down, meaning our first derivative is going to end up looking like negative 6 times x squared plus 3 to the negative 2, and by the chain rule we also have to take the derivative of what's in the parentheses, so times 2x. Which means, let's rewrite this. Negative 6 times 2x is going to give us a negative 12x. And now we are going to bring the x squared plus 3 to the negative 2 down. So x squared plus 3 squared. So we've got our first derivative. And that's great. Now we need to find our second derivative, and we do have to use the quotient rule for this. It's just not going to work out quite as nice if we do something different. So step 3, we're going to find the second derivative. So we're going to use the quotient rule. The second derivative, it's going to equal the numerator of our first derivative, so x squared plus 3 squared, times the derivative of our numerator, so negative 12, minus our numerator, negative 12x, times the derivative of our denominator. So we're going to have 2 times x squared plus 3 times 2x, and all of that is going to be divided by our denominator squared. So x squared plus 3 squared is just going to be power of 4. Now I'm going to clean up what I have in my numerator. So to start rewriting this, I'm going to have negative 12 times x squared plus 3 squared, and then I'm going to actually multiply out what I've got on the other side. I've got minus a negative 12 times 2 times 2x. In fact, that's 12x. So we're going to write plus 48 x squared times x squared plus 3, all divided by x squared plus 3 to the fourth. And I do notice something up top. There's some common denominators I can factor out. So both terms in my numerator have a negative 12, so let's factor that out right away. And then they both also, well, let's just do the negative 12 for now. So we're going to have negative 12 times x squared plus 3 squared plus, in fact, not plus, minus 4 x squared times x squared plus 3, all divided by x squared plus 3 to the fourth. Now I also notice in the parentheses, everything happens to have an x squared plus 3. So how about we go and we cancel out 1 from each term. So I'm going to rewrite this on my next page. We're going to have negative 12 times x squared plus 3 minus 4x squared over x squared plus 3 to the power of 3. This is all still a continuation from our last slide. We're still in example 1. We can clean up what is in the parentheses. If we combine x squared and minus 4x squared, we're going to get negative 12 times negative 3 x squared plus 3 divided by x squared plus 3 cubed. And then I also notice that the stuff in the parentheses in my numerator, I can factor the negative 3 out. So we're going to end up factoring that out, and we're going to go negative 12 times negative 3, get a positive 36, times x squared minus 1 over x squared plus 3 cubed. So our second derivative is this. And now we need to move on to step 4. Set our second derivative equal to 0. So the only way this second derivative can equal 0 is if the numerator equals 0. So we're going to go 36 times x squared minus 1 and set that equal to 0. If we divide both sides by 36, we're going to be left with x squared minus 1 equals 0. We can factor it as a difference of squares, or we can add 1, get x squared equals 1, and take the square root of both sides, and get x equals both a positive 1 and a negative 1. So this helps us now to determine our intervals. So step 5, our intervals are going to be from negative infinity to negative 1, from negative 1 to 1, and from 1 to positive infinity. So we need to pick a value within each interval to test. So we can take negative 2, 0, and 2. So I'm going to have to go on the next screen for the work, but what we're going to look for is the value of our second derivative at negative 2 the value of our second derivative at 0 and the value of our second derivative at 2. Now, I would just go and use a calculator to do this. Why make more work for yourself? So, I'm just going to tell you what I got. When I used -2 and plugged it into my second derivative, I got 0.314. And since that value is greater than 0, that means on that interval we are concave up. So from -infinity to -1, we're concave up. When I put 0 into my second derivative, I got -1.3 repeated, so -1 1/3, and since that is less than 0, on that interval we are concave down. So from -1 to +1, we're concave down. The last number I had to check with my second derivative was 2. When I put that into my calculator, I got 0.314 again, which is greater than 0, which means on that interval we are concave up. So from 1 to infinity, we are concave up. We determined the intervals of concavity, and we're now done with example 1. I know that took a long time. We have 2 more topics to talk about, points of inflection and the second derivative test. I'm going to try to get them both in our next video.